Hi, I'm Herb Gross, and welcome back once again to our Math as a Second Language video series, where today we will introduce the concept of decimals. Decimals are essentially what would have happened if, when we introduced fractions, we had insisted that they follow the place value enumeration method. In other words, if we had extended the whole number system to include fractional parts, that the only fractions that would have been allowed, just as we allow tens, hundreds, thousands, would have been tenths, hundredths, thousands, etc. And for that reason, students always used to say to me, why couldn't we study decimals instead of fractions? They're so much easier. Well, they're easier only if you're memorizing. There's a few little problems that come up using decimals that you don't have when you're dealing with fractions. And if you want to be completely honest about it, decimals don't make sense without the concept of fractions first. In other words, why would you have fractional parts of a unit? Why would you even have tenths, hundredths, thousands, etc.? So at any rate, there's just enough difference between whole number arithmetic and decimal arithmetic to cause problems if you're memorizing. It's sort of analogous. This has nothing to do with our course per se, but in studying for my doctorate, I had to take 2 out of a choice of 3 foreign languages. And the languages were French, German, and Russian. I had German in high school, so that was an easy one for me to choose. Russian I had never knew anything about, but a lot of good work was being done by Russian mathematicians, so I wanted to learn that one. And what I discovered about French was that when it came to math, it looked almost like misspelled English. In other words, you weren't reading prose. When you look at equations and mathematical work, you can almost guess what the words meant. But there were enough subtle differences that you could get in trouble that way. So what I want to do is to try to develop the notion of decimals in as logical way as possible so that you see its connection to fractions and where the problems come in and the like. Now, you're already used to decimals in a way that was completely non-threatening. For example, when we write $234.56, okay? And what this tells us in terms of our money system is what? The 4 is modifying the number of $1 bills, the 3 is modifying the number of tens, and the 2 is modifying the number of hundreds. Okay? The 5 is modifying the number of dimes, and the 6 is modifying the number of cents. By the way, I don't know if I've mentioned this to you before, but the word dime is a corruption of the word decimal. See, deci, a tenth of, and the word cent comes from the Roman centum. So in other words, a dime is another way of saying 1/10 of a dollar. A cent is another way of saying 1/100th of a dollar. Okay? Now, if you didn't see the decimal point in this number here, meaning the decimal point just told me that this is what the nouns are that are inferred. If I leave these denominations out, notice that all I see is what? 2, 3, 4, 5, 6. 23,456. That's the adjective. Now, up until this point, we have always assumed that the digit furthest to the right is in the ones column. But now you see the digit furthest to the right is in the cents column. And so what we could say is that what we call $234.56 is 23,456 cents, okay? In other words, what happens is if you leave out the denominations, this is important, the sequence of digits is your adjective. Okay? And the noun that it modifies comes from whatever the digit furthest to the right is modifying. So let's just look at an example. I'm going to write down the numbers 2, 3, 4, 5, 6, 7, 8, and I'm going to have them modify certain nouns. The 2 will modify 100, 3 will modify the tens, the 4 will modify ones, 5 will modify tenths, 6 will modify hundredths, 7 will modify thousands, 8 will modify 10,000s. Okay? So if I see this, I don't have to worry about any decimal point. I don't need a placeholder because all the nouns are in here. If I leave the denominations out, all I see is what? 2,345,678. The 8 is in the 10,000s column. And so it means what? I can read this number as 2,345,678 10,000ths. And the decimal point just is a placeholder that tells me what separates the whole number part from the fraction part. See, what does the decimal point do? It does not change the sequence of digits. It does tell me what the noun is. Now how can I recognize what denomination that is? Well, I'm going to show you something interesting again. See, suppose you want to maintain a decimal system, and all you have are ones, tens, hundreds, etc. Okay? Now you say, what happens if I have a denomination less than 1? Well, notice that in going from right to left, you multiplied by 10 each time. So in going from left to right, you divided by 10 each time. 100 divided by 10 was 10. 10 divided by 1 was 1. 1 divided by 1/10 is 1/10. 1/10 divided by 10, a tenth of a tenth, is 1/100th, etc. So what happens is, and this is kind of interesting, is that the symmetry is not with respect to the decimal point. The symmetry is with respect to the ones place. If you look at the ones place, the column immediately to the left represents tens. To the right, it's tenths. 2 columns to the left, 100. 2 columns to the right, hundredths. And that's going to give us a clue as to where the decimal point goes. In other words, if I write 234.56, notice that there's two digits to the right of the decimal point. 2 digits. See, the number of digits tells you the number of zeros in the denomination. So since there are 2 digits, this would be hundredths. If I wrote this, there's only 1 digit to the right of the decimal point, so that would be called tenths, etc. So again, let's emphasize that. The sequence of digits is the adjective part of the quantity. The decimal point determines the unit. Now, what does that mean? Let's look at 0.9. It really means 9/10. 0.09. And, don't read this as point. Read it as not. I'll tell you why. See, 17 cents is less than 5 dimes. When you say 0.17 and 0.5, the 17 is bigger than the 5, greater than the 5, and there's a tendency to think that 0.17 is more than 0.5. What I want you to see is what? Because there are 2 digits here, it's 17 hundredths. Because there's 1 digit here, it's 5/10. So at any rate, look what happens. Here's 0.9. I'm going to do what I told you not to do, just to emphasize how I'm writing this. 0.09, 0.009. If I leave out the decimal point and ignore the zeros that don't mean anything, notice that the adjective in all of these cases is 9. See? But here it's what? 1 digit, it's 9/10. 2 digits to the right of the decimal point, 9 hundredths. 3 digits to the right of the decimal point, 9 thousandths. And if we write that as a fraction, you see what happens? The numerator will be the adjective. The denominator is a 1, followed by as many zeros as there are digits to the right of the decimal point. Okay? And this is interesting, for example, in terms of probability. Suppose I have 10 ping pong balls. Suppose I have ping pong balls that are either black or white, and I have 9 black ones. If there are 10 ping pong balls altogether, it means there are what? 9 black and 1 white. If I have 100 ping pong balls altogether, I still have the 9 black, but now I also have what? 91 white. If I have 1,000 ping pong balls, I still have the 9 black ones, but now the rest are white. That means there are 991 white ones. Now, in all of these cases, if I had to reach into the bag and pull out a black ping pong ball to win, I would have 9 chances of winning. But look what happens. In this case, I only have 1 chance of losing. This case, I still have 9 chances of winning, but I have 91 ways of losing. And here I have 991 ways of losing. So in terms of probability, the probability of drawing a black ball here, a black ping pong ball, would be 0.9, see 9 out of 10. Here it would be 0.09. You still have 9 ways of winning, but there's 100 outcomes altogether, so you would write it this way. And here you would still have 9 ways of winning. But there are 1,000 ping balls here. So the 9 is the same in all of these cases, but look how dramatically different the decimal point makes the answer. So let's just review one more time. I'll take the digits 2, 3, 4. If I write 23.4, it's going to mean 234 tenths, because there's 1 digit here. If I write 2.34, it's going to mean 234 hundredths, because there are 2 digits here. And if I write 0.234, it's going to mean 234 thousandths, because 3 digits, 3 zeros. And if I want to write this in the language of fractions, notice that 23.4 would be 234 tenths, 234 over 10. If I now did the long division, there's my 23 and 4 tenths. And isn't that how you read this? 23 and 4 tenths, okay? And again, as fractions, if you didn't see the decimal point, you would see 234. The 2 digits here tell you that the noun is hundredths. The 3 digits here tell you that the noun is thousandths, etc., okay? This is all mechanical so far. Let's see if we can do something that's a little bit more user-friendly. Let's invent a money system that's going to be based on place value. Okay? So we're going to have a pure base 10 money system. What does that mean? Well, in every money system, there has to be a smallest denomination. Right now in the English system, it's a penny, right? There's no coin, no denomination less than a penny. So we'll just call it an SD, because we don't know what country we're dealing with, etc. So SD stands for smallest denomination. So this is, you can have 1 SD, you can have 10 SDs, 100 SDs, 1,000 SDs. If this makes you feel uncomfortable, you can think of $1, $10, $100, $1,000. But now where dollar means the smallest denomination, it would mean that you haven't invented dimes and pennies yet. Now the problem is, let's suppose that in terms of the economy, something that used to cost 1 standard denomination has become so cheap that it should cost less than 1 standard denomination. Well, there is no denomination that's 1 less. I mean, how can you do this problem? If the smallest coin is 1 cent, how can something be a half a cent? And the answer is you just sell it at 2 for a cent. How could something be a seventh of a cent? Oh, you sell it at 7 for a cent. But you see, that makes it kind of awkward, because to pay 1/7 of a cent for something, you have to buy 7 of them. Okay? The same with 3 for a dollar. If you want to pay 33 1/3 cents per apple, and the apples are 3 for a dollar, you have to buy 3 of them. Because if if you only buy 1, they're going to charge you 34 cents or more. Okay? So the question comes up, we will eventually need smaller denominations, but we want to preserve place value. Well, if going from left to right means you divide by 10 every time, okay? So you multiply by 10 as you go from right to left. You divide by 10 each time. So the new coin is going to be 1/10 of a standard denomination, 100th of a standard smallest denomination, etc. Okay? And so you see what you're going to get is, in terms of a money example, look what happens, okay? You can 200, you would get, in terms of our money system, suppose we had just invented the dollar, $10, $100. Now we want smaller denominations. Well, we would have invented a tenth of a dollar, which we call a dime, a hundredth of a dollar, which we call a cent. And in the old days, they even had something that was smaller than a cent. It was 1/10 of a cent. It was called a mill. You see, a mill was a tenth of a cent, which means it's also a thousandth of a dollar. And remember that the Latin word for thousand was milla. So in other words, the way we would write $234.56 today, in the old days they would have written $234 and 567 mils. We're not familiar with that right now, but again, eventually things became so expensive that the mill dropped out. I think in Pennsylvania they evaluate property per hundred rather than per thousand, and so that what happened there is that they give the tax rate per mill, so many mills per hundred, to be equivalent to what we use here when we use 1,000 as the base for assessment. So again, even in the early grades, you can introduce decimals in terms of extending the money system. You could also introduce them by extending the concept of a percent. See, let's look at what happens to 6/7 on scales of 10, 100, 1,000, etc. 6/7 on the scale of 10, if you do this out, comes out to be 8 and 4/7 on the scale of 10. On the scale of 100, you still do the division again, and it turns out to be 85 and 5/7 per 100, which we've done before. Let's continue this process and see what happens. We just saw that 6/7 of 100 was 85 and 5/7. Let's do 6/7 of 1,000. Well, notice that when we do this, we say 7 goes into 68 times with a remainder of 4. Wasn't this exactly what we did over here? In other words, to go from one power of 10 to the next, we don't have to start all over again. All we had to do was tack on one more zero here and just carry the operation one step further. And if we wanted to do it per 10,000, put another zero here. Per 100,000, another zero here. So what we did was, we could say we invented the decimal point to tell us whether we're doing it on a scale of 10, scale of 100, scale of 1,000, etc. So using decimals, this would say what? The decimal point comes over here. This would say this is 0.8 and 4/7. So the adjective would be 8 and 4/7. And what's the denomination? One digit. This is all one number, so there's one digit to the right of the decimal point. And that's how this would work. Now, what we just did leads to the real serious problem of why it isn't such a great idea to try to use decimals as a replacement for common fractions. For that student who says, let's forget about fractions and do decimals. In fact, let's see what happens. I call it a fly in the ointment. Let's carry this procedure just a little bit further. We would say 7 goes into 68 times with a remainder of 4. 7 goes into 45 times with a remainder of 5. 7 goes into 57 times with a remainder of 1. 7 goes into 10 once with a remainder of 3. 7 goes into 30 4 times with a remainder of 2. And 7 goes into 20 2 times with a remainder of 6. And it looks like this is going to go on and on forever randomly. But watch what happens. This is never going to come to an end. There'll never be a smallest denomination where we can get the exact answer stopping here. Because look what happened. This problem started with a 6 followed by endlessly many zeros. What do we have over here? A 6 followed by endlessly many zeros. In other words, this cycle, 8, 5, 7, 1, 4, 2, is going to go on forever. And there's no way we can say, what whole number does this represent? What is the smallest denomination? There won't be any smallest denomination. No matter what number of denominations you invented, you would never be able to get 6/7 of a dollar to come out exactly. You'd have to keep inventing one denomination after another. But again, I think this lecture has become a little bit on the long side, so let's go to our practice problem. And our practice problem today says, which of the following two decimals represents the greater number? And I'm going to read this the way I told you not to read it, 0.1 or 0.098, and explain your answer, okay? So pause the video and see how you would answer this problem. Actually, all I want you to see in this problem is the adjective-noun theme again. You see, 0.1 means 1/10. 0.098 means 98 thousandths. As adjectives, 98 is greater than 1. But as quantities, 1/10 is more than 98 thousandths. Now, how do we know that? Well, to compare the adjectives, the nouns have to be the same. So since the 98 is modifying thousandths, we want the number up here to modify thousandths. So another way to write 0.1 is 0.100. In other words, this still says what? 1/10, no hundredths, no thousandths. But now we read it as 100 thousandths. Now the nouns are the same. 100 is more than 98, so 0.1 is more than 0.098. Again, the thing I want you to see here is that you can't compare the decimals until they have the same number of digits to the right of the decimal point. So in other words, to compare these, I would have to do this. Then I can see they're both modifying thousandths. If I wanted to do this in terms of fractions, 1/10 could be written 1/10 versus 98 thousandths. To get the same denominator, multiply numerator and denominator by 100. So 100 over 1,000 is bigger than 98 over 1,000. So again, be very, very careful to remember the adjectives aren't enough to determine. We need both the adjective and the noun, and the decimal point is what gives us the noun, and the sequence of digits is what gives us the adjectives. And so until next time, be well, have fun, and I'm looking forward to seeing you again soon.